Now we will cover the Spark Streaming module for real-time, or more accurately, near real-time stream processing. Let's compare batch and stream processing. Batch processing is the ability to process and analyze data at rest, or your stored data. It is request-based, bulk evaluation, and short-lived processing. And it is an enabler for retrospective, reactive, and on-demand analytics. Stream processing, on the other hand, is the ability to ingest, process, and analyze data in motion in real or near real time in the case of the Spark Streaming module. It is event for real time or microbatch driven for near real time, continuous evaluation, and long-lived processing. It is an enabler for real-time prospective, proactive, and predictive analytics to determine the next best action. If you want to have all data analytics, you need to combine both the stream processing for real-time and batch processing. There are two approaches to data insights. There's the traditional analytics approach, and there's the next generation analytics approach. With the traditional analytics, business users determine what questions to ask, and IT structures the data to answer those questions. This is well suited to many common business processes, such as monitoring sales by geography, product, or channel, extracting insight from customer surveys, performing cost and profitability analyses. It allows organization to answer questions that will be asked time and time again. And then there's the next generation analytics, or the big data approach. IT delivers a platform that consolidates data sources of interest and enables creative discovery. Then the business users use the platform to explore data for ideas, which allows them to ask any questions. It's a more analytic approach, where answers to questions inspire new questions to be asked. Both analytic approaches are valid and complementary. Spark Streaming is an extension of the core Spark API that enables scalable, high-throughput, fault-tolerant stream processing of live data streams. Data can be ingested from many sources such as Kafka, Flume, HDFS, S3, and more, and can be processed using complex algorithms expressed with high-level functions like map, reduce, join, and window. Finally, processed data can be pushed out to file systems, databases, and live dashboards. In fact, you can apply Spark's machine learning and graph processing algorithms on data streams. Internally, it works as follows. Spark Streaming receives live input data streams and divides the data into batches, which are then processed by the Spark engine to generate the final stream of results in batches. It is recommended that the interval for these batches, or more properly, microbatches, is at minimum half a second long. Spark Streaming provides a high-level abstraction called discretized stream, or DStream. It represents a continuous stream of data where either the input data stream is received from a source such as Kafka, HDFS, or S3, or it's a processed data stream generated by transforming the input stream by applying high-level operations. Internally, a DStream is represented by a sequence of resilient distributed datasets, or RDDs. Each RDD in a DStream contains data from a certain interval, as shown in the figure. Any operation applied on a DStream translates to operations on the underlying RDDs. For example, here we demonstrate converting a stream of lines to words. The flat map operation is applied on each RDD in the lines DStream to generate the RDDs of the words DStream on a 1-second interval. Note that this 1-second interval is also the batch interval, during which a system could receive no lines at all to hundreds or even billions of lines, depending on its processing capability. Here's a visual example of applying transformations over a sliding window. Window operations are useful, for example, in calculating a rolling average on your favorite stock, or in monitoring a web server and giving statistics over the last hour refreshed, say, every minute. Below the figure, we have a sample code on applying a reduce by key in window method adding the values within that 30-second window, and refreshing every 10 seconds. Before going over structured streaming, let's cover top 3 challenges in streaming data: consistency, fault tolerance, and out-of-order data. First, consistency. A distributed design can cause records to be processed in one part of the system before they're processed in another, leading to nonsensical results. For example, suppose an app sends an open event when users open it, and a close event when closed. If the reducer node responsible for open is lower than the one for close, we might see a higher total count of closes than opens in the database, which would not make sense. Second, fault tolerance. What happens if one of the mappers or reducers fails? A reducer should not count an action in a database twice, but should somehow know how to request all data from the mappers when it comes up. Streaming engines go through a lot of trouble to provide strong semantics here, at least within the engine. Finally, out-of-order data. In the real world, data from different sources can come out of order. For example, a smartwatch might upload its data hours late if it's not connected to a network. Writing reducer operators to assume data arrives in order will not work in this case. They need to be prepared to receive out-of-order data and to update the results in the database accordingly. So what do you have with structured streaming? First, you have high-level APIs for data frames, datasets, and SQL, which makes it the same for streaming as it does for batch. Second, you have event time processing, or a native support for working with out-of-order and late data. And finally, you have an end-to-end exactly once transactional processing and output. When talking about structured streaming, the concept of an unbounded table is very useful, where the new data in the data stream become the new rows in an unbounded table. Let's go over a quick example how structured streaming handles late arriving data. We're going to focus on window group aggregation on 5-minute triggers. Let me also quickly highlight the different intervals. The first one is from 12 to 12:10. That's here in these tables. The second one is from 12:05 to 12:15. This part of the table. And then the final one is from 12:10 to 12:20. What's important here is that this dog event that was generated at 12:04 actually doesn't arrive until 12:11. And once the trigger hits at 12:15, all the counts will be updated that it has seen up to this point, including the dog that occurred at 12:04, but hasn't arrived until 12:11.